All right. Actually, I noticed right before class that actually what it says we're going to talk about today is not what we're going to talk about. Sorry. I'll fix the lecture calendar in a minute. The slides are right. It's just we're not going to talk about classes and objects today. We're going to keep talking about recursive backtracking. But I wanted to say a couple quick things before we get started. So one thing I want to remind you guys about, I don't like to bring this up too often because I don't want to scare people or whatever, but I do want to remind everybody that we do run these like similarity checking programs to try to look for honor code violations on our homework assignments. And I think like 99% of people are not at risk to be in trouble about that, but I just wanted to kind of remind you guys that that is something that we do, and that if somebody turns in work that isn't their own work, it's pretty easy for us to notice that, and then that often leads to bad outcomes eventually for the person who makes the mistake of doing that. Now, I don't want to scare people who are not doing anything wrong. It's okay to, talk to friends. It's okay to share some ideas with other people. I don't want innocent people to be scared into, being worried that this will be an issue for them. I'm talking like Googling for the answer, copying and pasting it into your file. I'm talking about your friend took the class last year and they email you their solution and you turn it in. I'm talking about stuff like that, I just want to remind you that that's not okay, and that if you are stuck on assignments, we want to help you, and I don't want you to feel that you need to do stuff like that. And just to kind of visualize, I don't know if this is helpful to show this or not, but I wanted to show you that like I have this software that we run. This isn't exactly what it looks like, but this is kind of what it looks like, where it shows me pairs of programs, and it shows me how similar they were, and then I can look through the code. This is actually not a screenshot from this course. It's like a Java assignment or whatever, and it highlights the parts that are similar, and I can look through it, and I can see if I think anything's wrong with it or anything's inappropriate about it or whatever. And it's pretty smart software. I mean, even if you kind of move some stuff around and change some of the names of things and change some of the comments, it still notices and it still highlights them for me and stuff. And it's not just that similar programs are bad, or if your program kind of looks like her program and you're going to get in trouble. That's not the idea here. The idea is if they're really similar, and then I open them, and then they're similar in a suspicious way, like they're identical, or you've got the same exact comment as them, or you've got the exact same strange code as them in a whole bunch of different places where it doesn't seem likely that that could be a coincidence, then it starts to be concerning. And anyway, I just want to remind you guys to be careful, and it's important. And, look, you can find solutions to the assignments. It's really easy. If you open Google and you just type in, CS106B, word ladder. I mean, there's a whole bunch of people who post their answers to it. It's super easy, right? So that's out there. I can't get these people to take all these down. I can't. I've tried, and they don't want to. And the websites like GitHub are not willing to remove files by my request because I don't have any legal right to force anybody to do that. So it's totally out there. But like me and my people, we go scour through all these sites too. And so we know about all these. We know how to use Baidu, we know how to use torrents, we know how to use a lot of different sites. And so I'm not saying we're perfect at finding answers online, but I'm saying if you do this, I probably have seen the program that you Googled for, and I'm going to see that you match that program if you copy that program. So, again, I think I'm speaking to a whole bunch of innocent people and like one or two people who are like, oops, probably. That's probably about the number that we're talking about here. But I did want to make sure that kind of to remind you that this is important to me and it's important to our class. And again, the sort of positive message I want to take away here is like, if you feel stressed like you can't solve an assignment and it makes you tempted to Google for an answer to an assignment or something like that, then I guess I would encourage you instead to ask for help, and I'd be happy to help you. The TAs, the section leaders, the layer, we're all happy to help you in lots of different ways. That's what I'd rather have you do than this. If you or someone you know might have messed up and done something wrong, like copied someone's work, there is an option that we have in the course called an assignment retraction, where you can contact your section leader and you can say, I would like to retract my solution for assignment 2 or whatever. And that just means we throw it out. And you don't get any points for it. You get a 0 on it. But no one runs it through this. And if there's anything you did that you regret doing, you are not penalized for that. Now, having said that, I don't want 50 of y'all to retract your assignments after this lecture either, because chances are only 1 or 2 people did something wrong, you know what I mean? So only if you really truly realize, like, oops, I copied and pasted somebody else's work and plagiarized that person. I don't want to get suspended from Stanford, and they are likely to catch me. Oops, what can I do? As long as we haven't processed the data and accused you of anything yet, you can still retract your submission, no questions asked, okay? So anyway, those are, I just wanted to remind, I said a lot of those words at the start of the quarter as well, but I wanted to bring it up again because I think the best way to handle this kind of stuff is prevention, where you don't do it, or if you do make a mistake, you sort of undo it. And then there's, I don't like dealing with this stuff. This isn't fun for me or for us. And I think most of the time when stuff like this happens, it's just somebody who makes a mistake. They make a bad decision because they're panicked and they're stressed, and it's due in an hour, what can I do? They make a bad decision. So anyway, does anybody have any questions about this? Again, I'm not trying to spook all you guys, but I wanted to just remind you that this is important to me. Do you have any questions about all this stuff, any of the stuff that I've said, or any comments about it? No? Well, if you do later, please let me know. I'm happy to answer questions. The fact that we allow pairs in the course is not directly to do with the honor code, but I do think if you're struggling, working with a partner can help, where instead of needing to Google for an answer, you and your partner can work together to get unstuck. So that's another thing you can do if you're struggling or stuck on an assignment. Okay, I'm going to move on. I figure you guys get what the message that I'm trying to send here. I'm going to go back to some lecture content. We're going to learn more about recursive backtracking. Tell me something about recursive backtracking. What do those algorithms usually look like? What sort of steps do you typically see in a recursive backtracking algorithm? Somebody raise your hand. Yes?
For each possible move, select an option, see what it does, and then unchoose it.
Sure. For each possible option, select it, and then see what can happen after that, and then unselect it. I use this choose, explore, unchoose vocabulary. What you said is identical, basically. I think I heard some of you kind of whispering that as well. Yeah, that's typically the idea. So I'm going to look at some more problems today, and we're going to see how we can solve them with recursive backtracking. Before I launch into any new problems, I wanted to talk about one aspect of style that comes up a lot with recursion that I think I've shown a little bit about in the past, but I don't think I've emphasized it very much, so I want to talk about it now. I want to talk about a term called arm's length recursion. You might have heard this in section, or you might have heard it in the layer. Arm's length recursion is a bad programming style where people are writing recursive code and they add unnecessary complexity to the code. They add unnecessary tests. Usually this means if-else kind of statements that don't need to be there. And typically the tests that are added, the unnecessary tests, are sort of avoiding making recursive calls, avoiding another level of call in the recursion. But if the student would rewrite the code in a slightly different way, they wouldn't need to make these tests. The reason it's called arm's length recursion is it's sort of like you're keeping the next call at your arm's length. Like, I don't want to make the next recursive call unless I test if, and then I'll make the next recursive call. Usually there's another way of structuring code like that that's more elegant. So that's the general concept of what this is, but I think it won't really make sense until I show you a specific example. Okay, we did the maze escaping function on Wednesday. And the code that we wrote for that, where is it? Looked like kind of like that. We said, well, if you're out of bounds, you can't. Then you escape. So true. If the square that you're on is not open, if it's a wall or it's already been visited or something, then false. I can't get out from here. Otherwise, I'm going to sort of choose, explore, unchoose. I'm going to mark and try to escape, and then unmark or taint afterward. Okay. So that's kind of what you said, all the different options. I'm going to choose, explore, unchoose each of those options, right? This is sort of the good way of writing this code. By contrast, let me show you the arm's length way. The arm's length way would be, I'm not going to make any recursive calls unless I think those calls would be good recursive calls. If you look at this code, you'll notice it just tries to go all 4 directions, right? With those OR statements in blue. But haven't you thought about, like, wait, what if I shouldn't go up? What if I shouldn't go left? What if there's a wall over there? What if over that way is already been visited? I probably shouldn't make those recursive calls if those directions lead to something bad, right? That's a mindset a lot of students have. And so what they'll do in their code is they'll say, well, if the square to the right of me looks good, then I'll try to explore to the right of me. That seems super rational, super understandable for a student to want to write the code that way, right? But the real zen of all this is just go for it. Who cares if to the right of me is a wall? Who cares if to the right of me is out of bounds or something like that? Let's just make a recursive call over there. What will this code do if that place to the right of me is bad? What will this code do? What? Like, is this buggy code because I'm making recursive calls that might go to bad places? What do you think?
What if return false?
It'll make a recursive call over to the bad square. It'll see that it's at a bad square. And it'll immediately bail out and come back with a return false, right? And you might say, well, that's an unnecessary call then. But it's not harmful. It just real quick checks and comes back. If there's nothing to do up there, it real quick checks and then comes back. And that turns out to be much more elegant. If you look before you leap, if you put your recursive calls out at arm's length, the code looks more like this. Well, I'll mark my square. If the square above me is in bounds, and if it's open, then I'll try to escape from there. And if the square below me is in bounds, and if it's open, then I'll try to go down there. And if the square to the left of me is in bounds, and if it's open, do you understand? And so, I mean, I actually didn't run this. I don't think it even works really. But like, this is the sort of way that the code starts to look. Don't do this. Do you see why this is bad? I mean, I'm repeating a whole bunch of tests. Is it in bounds? Is that one in bounds? Is that one in bounds? Is that one in bounds? You don't need to do that. Just check if your current square is in bounds. What I have here as my base cases. Do you see that? This code is afraid of hitting a base case. I'm afraid of going to a case where I would have to stop and turn back. I'm afraid of going to a case where I would go out of bounds. No, just go for it. Just do it. It'll be okay. Your code will come right back. So this is the idea of arm's length recursion. If you've heard that term, you know, I'm trying to clarify what that sort of means. I thought this example would do well to illustrate the concept because it's so clear that you have to repeat a lot of tests in this style. So that's what arm's length recursion is. Do you guys have any questions about that? Does that make sense? You have a question, yeah.
So is it a matter of being immediate in your recursive cases instead of preemptive?
Being immediate versus preemptive. Well,
In your immediate circumstance as opposed to trying to foreshadow other circumstances.
Well, I think what's really the issue here, like what's like bad about this code, is that you know, you should be concerned about you. Your call should be concerned about the part of the problem that you are handling. My call is going to handle my square. So if my square is out of bounds, if my square is not open, I will react to that. The other calls should handle their square. So if I call to the right and the right is bad, he should worry about that. If I call to the left and the left is bad, that call should worry about that. And so that's the principle here. This example also introduces a lot of redundancy by having the arm's length solution. Some arm's length solutions are not quite so redundant as this. But even if it's a little bit less redundant than this, it's still the principle of the thing. You should handle your part of the problem. The next call should handle the next part of the problem. You shouldn't be reaching into their part and trying to preemptively decide what they do and whether they should even be called. You know what I mean? Now, this might seem to be in conflict with something I told you before. I think I told you before that when you're doing backtracking, you don't want to make unnecessary calls. I even wrote a program that had an evil global variable that counted the number of calls that we made, right? But so you might say, well, this version here is going to make a lot of extra calls because it's going to call into these dead ends and come right back. Those kind of calls are not the kind of calls we're trying to minimize. Those kind of quick jumps in and out kind of calls, they have small performance overhead. They're not very much. Don't worry about that. The kind of calls we want to avoid are the ones that lead to a tree of things that aren't even worth looking at, that we shouldn't have had to explore in the first place. So this stuff I'm talking about right now is not in contradiction with that concept of limiting a search to reasonable search space. Okay? Do you have any other question about arm's length recursion? Thanks for waving at me so I saw the hand up there. Anyone else with questions? It's kind of related to, I've talked about this in slightly different language in the past. I think there's been cases where, like, I said, well, what's a number of dice that are easy to roll? What's a a string that is easy to see if it's a palindrome or whatever. And often students will give me the sort of one case. They'll say one die is easy to roll. And I'll say, oh, you guys aren't being lazy enough. There's an even easier number of dice that are easier than one die to roll. And you'll say, oh, 0 dice, you know. And I think it's the same kind of model. It's like, let the recursion go all the way down to a base case that essentially doesn't have to do anything, that just exits. Like that's sort of a similar concept and design strategy here. Okay, well, anyway, you can look at that more if you have more questions about that later. I want to look at a new problem. This one's called sublists. So we're past a vector of strings, and I want to print essentially the power set, if you know that term, all the possible different subsets of the vector. There it is. Print them out in any order you want, but I want to see them on the console, one per line. Now, this looks like some kind of vector processing, pulling things in and out of a vector type of a problem. So it might be helpful to look at the last problem we did that was similar. We did this permutations problem last time. Remember that, where we rearranged all the different orders of the elements? So maybe I should open that up. I can open the lecture code from last time. Where is it? Permute. Here. Looks like this. So this one keeps a set of all the things that we've printed. We don't have to do that. But basically, we remember this. We process the vector. We pick out an element and put it into a chosen set. And then we explore. And then we put it back after we unchoose, right? So that's the code for permutations. Now we have to do subsets. So let's go to my Qt Creator project. I need to write this function here called sublists, subsets, whatever. Do you have any suggestions for me? What are some of the things I should think about first when I'm writing a backtracking algorithm? Base case? Yeah, that's definitely one of the things I need to think about. I think there might be something that supersedes that as well. How do these solutions usually look? What are some elements we usually start working on? What do you say? What I have chosen? Right. How do I know that? How do I keep track of that? Sorry? Well, for example, here, let me zoom it out a little. So there's permute, and that's our code. So I think you're totally on the right track. I'm just trying to pull a little more out of you. Like what do you mean by I have to know what I choose? What does that mean?
So you would need to like choose, explore, then unchoose. So by doing that, you would probably use the loop to add. So you have your if for your base case and your else, and then within the loop is where you would do something like add it to the vector.
Okay, so add the things that I choose into some kind of vector so I can keep track of them. And in terms of the mechanics of how that's going to work, I think we probably want a structure like this, where because there's no place for some other vector in this existing function that we have to write. So I think that would mean we probably want to mirror this idea of having a helper function, right? And so that's I think maybe the first thing you probably want in a backtracking problem is figure out what the choosing is. What am I choosing? I guess I'm choosing elements from this vector to be in this subset. And I got to keep track of all that. And just like you said, that seems like I could put the things I've chosen into a vector. So let's make a helper function called void sublists helper, and it'll take the same parameters to it as the original function, but you said I want to keep another vector of what I have chosen. Seems like a good idea. So now in the real function that we need to write, I'll declare a vector of things that are chosen, and I'll call sublists v comma chosen, sublist helper, because initially I have not chosen anything, right? And why is that underlined like that? Do I have some kind of, oh, I don't have a closing bracket here. Okay, great. So that's a good start. Now, those of you who said base case, I'm happy to think about base cases now. What's a vector that's easy to do the sublists of? An empty vector, okay. So if V is empty, well, that's a base case. We'll figure out what to do there in a minute. Else, now this is usually the recursive case, right? And we need to, for each possible choice, we need to choose and explore and unchoose, right? Choose and explore and unchoose. Now, the thing about backtracking problems is sometimes it's tricky to figure out what the possibilities are, what the choices are. What is the unit of work that each function call is going to take care of? Some problems, that unit of work is obvious, like escaping from a maze, it's one square, or if it's a string, it might be one character, or these kind of things. Maybe for a vector, it seems, okay, it'll be one of the elements of the vector, or something like that. Here's the output I wanted to produce. Now, you mentioned using a for loop, so I think what I could do is I could say, well, okay, for each choice, that means for each element, right? V dot size for each element in V. I could write some code that will choose, explore, unchoose that element. I'm a little worried that this code's looking a lot like the permutations code. It looks almost like I'm just sort of repeating that code. And I mean, if I rewrite that code, I'm going to get permutations, not sublists, right? So there's some kind of difference between the two that I need to be more mindful about. Let's look at this again. No, wait, what's my next slide? Okay. If we write code that sort of loops over the elements and grabs each one and chooses and explores and unchooses it, I think what will happen if we do that is we'll end up with a decision tree or a call tree that looks kind of like this. We start out having chosen nothing, and our vector B, all the elements available are these 4. And then our for loop will decide who goes first, Jane or Bob or Matt, and then our next call will decide who goes second. Bob follows Jane, Matt follows Jane, Sarah follows Jane. If we do this, if we loop over the elements and choose them and explore them and unchoose them like this, I think that leads to permutations. I think that leads to Jane Bob and Bob Jane. You see that? I don't really want Jane Bob and Bob Jane. That's orderings of elements. I want this. I want all the possible combinations of people being present or not. You know what I mean? So I guess, again, it comes back to this question of what are the choices? If I'm going to process an element of this list, what is it that I'm choosing? Like permutations is choosing where the element is, what order it is going to be in the result, right? That's what you're choosing, basically. What are you choosing when you're deciding to explore different sublists? Let's see, somebody I haven't called on. Yeah, go ahead.
Choosing which name to get rid of out of your head.
Which names to get rid of? That's an interesting way of thinking of it. What if you look at these 2 columns of output? I mean, I put the output that way kind of as a hint. It's sort of a hint, right? What's the difference between those 2 columns of output? Column on the left has Jane, and the column on the right doesn't have Jane, right? So imagine I said to you, hey, function call. You're a function call. You're a human function call right now. You're in charge of Jane. What are the things that could happen for Jane? What are the things about Jane that might be relevant to the answer we find or the output we find? You said we're deciding who to throw out. So if you're handling Jane, I think what that means is you're deciding whether Jane is in the output or not. You're deciding whether Jane is in the subset or not in the subset. And we're going to want to explore both of those things, right? Well, let's print all the ones that do have Jane included, and let's print all the things that don't have Jane included. So what I'm trying to show you here is that the choices in this problem are not about looping over all the elements and like adding them to another vector, because that has more to do with order. Instead, each call should decide include or exclude. That yes or no choice is the responsibility of each function call. I don't know how to print a bunch of sublists, but I can manage Jane. I'll decide if she's in or out. And the next call says, I don't know how to print sublists either, but I can handle Bob. I'll decide if Bob is in or out. And so on, until we have chosen all of those things together. So the decision tree I don't think should look like this. Instead, I think it should look more like this. You might not even see the difference for a second, but the fork in the tree is not 4 possibilities, Jane and Bob and Sam or whatever. It's Jane's in or out. And the next call is Bob is in or out. And so on. Different call tree, different decision tree, 2 branches, not 4. Does that make sense? Because that's what we're really choosing. We're choosing membership. We're choosing who to throw out. Can we try to translate this into C++ code. This is the right overall algorithm or idea here to solve this problem. What are the possible choices? Well, let's keep in mind what part of the problem am I solving. If the vector v consists of, Jane, who are the people? I think I'd have this memorized. Bob, Jane, Bob, Matt, Sarah. If I'm the first call, my job is to process Jane. If I'm the second call, my job is to process Bob. So each possible choice for my call means each possible thing I could do with Jane, or each possible thing I could do with Bob. So I don't know, give me some code here. What sort of stuff can I be doing to implement these ideas that we've been talking about? How do I indicate to the other calls, hey, you guys, I got Jane. I'll take care of Jane, so that they don't try to take care of Jane? How can I sort of lock on to that, make it clear that that's my responsibility? What do you think? Yes? Remove her. Okay, that sounds fine. So how about string s equals, I guess we could just grab the first person out or something. So vector dot, I think it's called, there's a method called front that gets the 0th, or I could just say v0. That'd be fine. v0. And now just pull her out of there for a minute. We'll put her back, but for a minute, let's pull her out of there. v dot remove 0. Now, in other algorithms we've written, I said remove I or for loop int I. No, I don't think actually we need to do that. We'll take the first person, and we'll handle them. So now, what are the possible choices? We already talked about that. The choices are string s should be in the output, or string s should be excluded from the output. Those are the two choices. So we don't want a for loop anymore. What we really want to do is try with s, then try without s. So how do I indicate that I want to keep this person, that I want to have them in the sublist? What do you say? Add them. So you said add them back in. I think that would mean to put them back in V, but I want to put them in the other vector, chosen, because that's kind of where I'm going to put my sublist that I'm building. I get what you're saying, because like you could just leave them in their original vector, but I just, for conceptually speaking, it's kind of like, let's take all the people I'm keeping and put them over here, and that's how, if it's okay with you, that's how I'd like to do it. So how about chosen dot add s, so put Jane in the sublist. Okay, now I have to explore. How do you explore? Don't say base case. It's not base case. Yeah, with the red. Check it, yeah. Make a recursive call. Yeah, okay. Sublists helper. And I'll just pass the same V and the same chosen, but they're changing their state. So the next call will see a different state than I do. Okay. Now, remember how I have to try with S and I have to try without S. How do I try without S? Yes, go ahead. Thank you.
Can we do the recursive call before we add s to chosen?
Oh, we could do that. So what you're saying is try first without S and then try with S? Sure, okay. So what you want to do is explore recursive stuff without S in it first, just because that might save us a line of code or two. Okay, sure. So I just explore sublists that don't, I remove person S from consideration and I don't put them in the sublist, and I explore what could follow that choice. Then the recursive call does exploring and it comes back. Now what should I do? I should put them in the sublist? Then what? Call the helper again. Sure. So, I mean, maybe this structure looks... I'm doing this problem for a reason. The reason is because the way the code is structured looks different than a lot of the other problems we've done so far. I think the choosing, it's like, how do I fit this into my mental model of choose, explore, unchoose? And I guess what I would say is like, choose and explore without S, and then this is like choose and explore with S. You know what I mean? Like choose, explore, unchoose. I'm sort of doing the choose, explore, choose, explore. I have to do the unchoose part. How do I unchoose? Sure, go ahead. Yeah. Put the value S back into the vector V that we pulled out. Yeah, basically put our toys back where we found them. Take the toy back to the carpet. Put the cookie down. Never mind. Insert at element I. Let's put string S back into the vector. We're almost done. I think we've got some really good stuff here. There's an important piece that's missing. Yes? Sorry, didn't define what? Oh, into I. We didn't define I. You're right. So that's not what I was meant to say, but you're totally right that should be 0. We removed from 0, so we should insert at 0. Totally right. There's another thing missing. Because, we're going to be doing all this work, all these recursive calls. Those are building to something. Something very important. It is the base case, yeah. In the base case, we need to print the culmination of all of the choices that we made. See out, chosen, end. Okay? Could this possibly work? Whoa. Oops. There's too many. I've invented a human cloning of some kind, actually. That's a little bit of a bug. It looks like it's doing interesting things, but what needs to be done to fix that? The vectors that got printed out got bigger and bigger and bigger. So this chosen vector is growing out of control. Do you see what needs to be done? Yeah.
You used to initialize chosen as an empty exo.
Okay, so the chosen is empty down here, but then when I add people to it, once I'm done exploring that possibility, I don't want them to be in there anymore. I want it to be empty, or at least I want it to be free of that person. I mean, basically down here when I unchoose, I need to say chosen.remove back, remove the last element out of the vector. So now if we try to run it again, what do we got? Nobody, Sarah, Matt and Sarah, we got Bob, is this working? I think the output is in the opposite order as it was on the slide, but I don't care. The order is not the key concept. This, I believe, is all of the subsets of the vector. So we did it. Anyway, the main point here is that there's a couple of main points. One is that you don't always have a loop. Do you see this? Like your recursive backtracking code might not have a loop. And it helps to understand why a code for backtracking might have a loop versus might not having a loop. It has to do with what are the different choices that we're looking through. In the maze problem, it also didn't have a loop. Because to describe the 4 choices, we would just make 4 calls. Go up, go down, go left, go right. There wasn't an easy way to describe those 4 calls using a loop. So we just wrote them all out. Here, similarly, there are 2 calls we need to make. Keep the person, exclude the person. And there's not an easy way to just loop to do those 2 things. So we'll just say it. Remove them and make a call. Put them in and make a call. Doesn't need to be expressed as a loop. It's a fork in the road. Yes?
Why do you have to insert S into the original vector again?
Oh, why put S back? That's a good question. Let's not. Let's see what happens, right? So I think what happens there is that we will not be able to include the person in more than one branch of the tree if we do that. Because there are branches that have Sarah and these people or Sarah and those people, and I guess my suggestion would be to put some print statements in here later and kind of trace through the different calls that are made. Like basically this forbids 2 branches of the tree from having the same person in them, would be my comment about it. Yeah. So anyway, that's the sublists problem. And you'll see, if you haven't, most of you have already been to section, but I think on the section handout you would see similar. That some of those section problems have loops and some of them don't. And I think a key light bulb moment, I think, for students who are practicing recursive backtracking is like, can I figure out whether I need a loop on this problem or not? It seems like a small thing, but it's actually a really big deal because it means you're seeing what the choices are that your code needs to make. And if you don't have the right set of choices that you're trying, you're not going to get the answer that you're trying to explore in the first place. So it's a big thing. One other question. Yeah, go ahead. Oh, could I clear the chosen vector? I could, except I think in general, it's sort of similar to the principle I mentioned earlier of like your call is responsible for your stuff, your work, and not others. I think if you clear, what happens is there's some previously chosen stuff that I don't want to throw away. A couple of choices were made, and then it gets to me, and I'm going to try to do some further stuff. And then when I'm done with my stuff, I'll put things back how I found them. I'll put everything back to the state that it was when my call began. But if I go clearing stuff that other calls did before me, they would not expect me to do that. And so then their call that's trying to do work might get confused or get messed up by that. So I think that would break the, I'll do it just to illustrate. I'll say chosen.clear. I'm pretty sure we're going to see some output that doesn't look right. So I mean, it doesn't build to the full vector because previous calls are wiping out, next calls are wiping out things that were important to previous calls, I think is what's happening. So, okay. These are great questions. This is how we understand these things. Trying variations, why doesn't this version work or does that version work? These are great questions. Any other question about this problem? Okay, I want to do one more problem. I got about 10 minutes left. I think we can do it. I want to do a problem with you guys called the 8 queens problem. This means you've got a chessboard. You guys know probably that if you put a queen on a chessboard, it can attack or move into 8 directions, up, down, left, right, and the 4 diagonal directions. So the goal of this problem is it possible for me to put 8 different queen pieces on board such that none of them are able to see each other to attack? That means they can't be exactly diagonal, they can't be exactly sideways or up and down from each other. Now, I mean, look, spoiler, answer is yes, there, that's how. So it's not that the answer is a mystery. It's just like, could I write a program to find this if I didn't know the answer? And also, it might be fun if I could have a general answer that what if it were a 9x9 chessboard or a 5x5 chessboard? Is there a solution to the n queens problem for an n by n chessboard? Okay, I want to do this with you guys with recursive backtracking. Well, choose, explore, unchoose. What do you think the choosing is? What's the choice that you make in each call on this method? Just a wild guess. What do you think? Place 1 queen? Is that what you said? Yeah, like, I guess what you would do is you'd sort of choose to put a queen in the top left, and then you explore trying to put more queens after that, and then you unchoose if they could attack each other, if it didn't work, something like that, right? Choose where to put 1 queen. So you could imagine a version of this code. Oh, okay, whatever. I got my little animation there. You could imagine a version of this code that's like for each of the squares, choose to put a queen there, and then explore, and then if it doesn't work, then unchoose and try somewhere else, right? But look, that's not the most efficient way to do this, because there's a whole bunch of, we talked before about trimming down the space of searching, not making a lot of unnecessary trees of calls. This version of this makes a ton of unnecessary calls. It's not the way to do it. We need to be a little more efficient if we want an algorithm that runs in a reasonable amount of time. So, there are some simplifying observations that we can make. If you look at the solution here, what are some things that are true about this solution and that are likely to be true about any solution that is going to be correct? What do you say?
You need 1 queen in every row.
1 queen in every row and 1 queen in every column, right? There can't be 2. And there also can't be 0, just by what we might call the pigeonhole principle. Like, there has to be 1 in each for them to be safe from each other. So the fact that there's 1 queen in every row and 1 queen in every column, we could take advantage of that. Rather than searching every single square, we could say, well, I know 1 queen goes in the first column, and 1 queen goes in the second column, and 1 queen goes in the third column. So let's explore where to put each of those within that smaller search space. Instead, let's do more like this. Loop down the first column and choose all those options. Then explore looping down the second column and choosing all of those options. So instead of looping by 64, we're looping by 8. You can be even more clever than this if you wanted, but this is enough of an optimization that it'll make the algorithm run in a reasonable amount of time. So the problem becomes each call decides where to put a queen. And you said in a given row. If it's okay with you, I'll do it as a column just because that's what my slide draws, but it's totally, you could loop sideways or you could loop down. I'm going to say each column has 1 queen. Each call, each function call decides where to put that queen. So I want to write this with you guys. We don't have a ton of time. I think we can finish it. I have a class called board, like a board, a chessboard. I'll pass you a parameter of a chessboard, and it has a size, And you can ask if a square is safe. That means if I put a queen there, would all the queens be able to attack each other or not? You can also place a queen on a square, and you can remove a queen from a square, and you can print the board out to see out or by calling two string. So this will help us with some of the nitty-gritty details of queens diagonally attacking each other and stuff. So I want to write a function with you guys called solve queens. I'm going to open it right now. Solve queens. Here it is. And it takes this board, this chess board, as a parameter. So help me. Each call is supposed to decide where to put a queen in a given column. The first function call does the first column, the second function call does the second column, and so on. How do I begin this sort of a process? How do I tell these function calls what their duty is to do? Each function call needs to know what its work should be, right? What are your thoughts? How do I get started attacking this problem? What do you think?
Just a question, has the board already been initialized as 8x8?
Board is ready to go. I've got a board up here of, I guess it says 5, but I mean, we would probably want to set it to 8. Board 8x8, yeah, ready to go. So they're passing us an empty chessboard, ready to play with. How does each function call know what its duty is to do? The first column is supposed to be the first function call. The second column is supposed to be the second function call. How do the calls know what they're responsible for? What do you say?
Right now, they kind of don't. Like, we don't have the help function that we've been setting up in our past factor.
Okay, well, so you said the calls currently don't know what they're supposed to do because we don't have enough information. So you said helper function. I think that's great. Let's write void solve queens helper. And usually the helper takes the same parameters as the original function, along with any extra information that the function call needs. What extra information would you like to give it? What column this function call should handle? Great, okay. So when you're first getting started, you call solve, you got to get everything going. So you pass the board, what column is the first function call responsible for? The first one. Now, to be honest, I can't remember, is it 0-based or 1-based? I have to go peek at this for a second, because I thought I have this memory that it might be 1-based. No, it's 0, 0. Okay, never mind, sorry. I wanted to make sure we didn't pass 0 when it wanted it to be 1, because I think the slide says 1 through 8. I should probably fix that, but whatever. So the first function call is responsible for the 0th column. Now remember our algorithm. For each choice, choose, explore, unchoose, right? What are the choices I can make, my function call can make, for the given column that I'm in charge of? What are the choices? What are the options? In the green, yeah, go ahead.
What if we choose the directions that the queen can go, so diagonals and then up, down, right?
Well, it's less about the attacking directions of a queen, like the diagonal red arrows. It's more like where can I put the queen? Where would that make her be able to attack? I think the idea is if I'm handling this column, I could put the queen in any of the 8 rows. And then in the next column, I could put that queen in any of the 8 rows. And in the next queen, I could put that in any of the 8 rows. Some of those rows are bad and won't work, but those are the 8 options available. Do you understand? So the choices, the things we're for each choicing over are the 8 columns. For each row, from 0 to board size, which would be 8, less than 8, row plus plus, those are the options. Choose, explore, unchoose. Well, how do I choose? I put a queen there, right? Board dot place a queen at this row and this column. Explore. How do I explore? I make a recursive call, right? So I say solve queen's helper. Board. What do I pass to the next call? They are responsible for the column after me, right? If I'm column 3, they're column 4, etc., right? When this comes back, unchoose, You tell the board, I don't want the queen to be there anymore. Board.remove, row, column. We're not quite done. There's some pieces missing that are important. There's something missing from my recursive algorithm. What is it? Base case. Yeah, of course, right? What's a good base case? When do I stop having to do all this recursion-y stuff here? What?
Last column.
Once I get past the last column, once all the queens are placed down. Yes, so if the column I've reached is exceeding the board size, then what does that mean? What should I do here? It means I've put all the queens down on the board, right? So I should probably show the board. I should see out the board indle. But wait, I don't want to print boards that are invalid, that the queens can hit each other and stuff, right? So how do I avoid board states where the queens can hit each other? There is a method in the board class called isSafe. Is it safe to put a queen somewhere? How do I incorporate that into this code to make sure that I don't explore bogus outcomes? Yeah, go ahead. So before we make calls, let's make sure if it is safe to put a queen at that row and column. Bob and Matt and Sarah, wow. Give me 20 seconds here. I know it's time to go in a second, but. Uh-oh. What did I do? I think this should be else. How about that? Oh, sorry. You know what I did? I'm sorry. I wrapped this whole thing wrong. If it's safe to put a queen there, place it, solve, and then unplace it, right? I've got my order of operations wrong. Let's try that again. A bunch of answers spit out. It actually prints all of the solutions to the problem. The last thing I'll show you as we leave for the day, for the weekend, is if you want to see the code animate, up here I've got this function called setDelay, where every time you place a queen it pauses for a second and you can watch the algorithm. So look at that. So do you see what it's doing? It's a little stuttery because our libraries are kind of poopy, but it's trying all the possible options. And what you'll notice as you leave is the ones further to the left stay put longer because we explore all the things that could follow them. That's why the code ends up looking the way that it does. I got to stop there for now. Have a great weekend. Thank you guys. Homework 4 is up when you want to look at it. I'll see you Monday. Thanks.